Once again, what do I activate? What's the name of the program? Desktop.
Yeah, it's okay. We can do this every week. One button.
I know, but I keep forgetting how to. You can't do it before I log on.
Oh, yeah.
Yeah, you can't do it before I log on.
It only takes 2 seconds, so it's okay.
Thanks. Okay, this is the task for you. Okay, I don't want to scare anyone. So I just randomly selected 5 groups, and I decided to call them front, back, middle, right, and left. Not because I want to check knowledge of an individual. It is more about checking the acoustics of this room. You see these people with cameras. Sometimes they're there, sometimes they're over here, and we are not sure actually where is the best place that my voice is heard. So I'm going to check, the way you answer this question will tell me where the acoustics is the best. So those who have these sheets of paper, of course, consult people around you, and you have about 3 minutes to sketch the step response. And then we will just compare those results. I will actually ask these three gentlemen here to be my expert panel to help me judge which one is the best and where, in which corner the sound is best. So the rest of you, try to answer this as well. No one is stopping you from trying to sketch the response, step response of an overdamped system. Okay, so are we progressing? Okay, maybe we should check what you have done so far. Doesn't matter if it is not complete. Okay, let's see quickly. A red pen like an exam, but no marks. Don't worry. Okay, so this is the front group. Overdamped system. Did we say overdamped? Yes, overdamped. So this is okay. Overdamped system has two real and different poles and step input. So this is correct. Okay, now they're trying to do partial fractions, although this case exists in the tables. So it is a bit of waste of time, nothing wrong so far. Okay, this looks right. I can't check every single coefficient here. This looks right, but this doesn't really look right. The graph, the actual question is sketch, so the sketch is not that good. Possibly, well, it looks exponential, which is probably the only good thing about this graph. So experts, what do you say out of 10? 6? 6, okay. So that's front. The rear, actually, this is a very good sketch of an underdamped system. But it's not overdamped, okay. They did try. Okay, they reduced the overshoot, they reduced the ripple, they shortened the settling time, so it's not that bad, but actually the answer is wrong. So 2 marks for improvement. Okay, this was really wrong, this is a bit better. 2 marks. Rear. Back, well, actually, similar to this one, just more of an overshoot, more oscillations, that's 1, I guess. Yeah? Well, why I'm asking you? I'm making all decisions here. I want you to be blamed. Okay. For ecological approach, let's not waste any ink, it's 0.5. Oh, this looks good. This is actually correct. However, yeah. You know, what is this? What is the function here? 9.5. Yeah, this is correct. The system is overdamped, so it must be exponential. And because it is a step response, it approaches a steady state value which is not 0. Okay, so this is a correct answer. Right, now back to the question of acoustics. From now on, I expect you all to be on this side. Okay, if you want to prosper in this subject, this is the side for you. Okay. Okay, good. Yeah, so we checked 5, right? A little bit more about lecture 9, and I hope to have a little bit of time for the practice paper I gave you, and of course, most of the practice, most of the revision will be on Tuesday. So we stopped here. We described the relationship between the placement of the roots in the S-plane and the behavior of the system. So whether it is, so just to confirm what we had an overdamped system. We had 2 roots, something like A and B. So 2 real and different roots, both negative. That makes a system an overdamped system. So therefore, we have exponential behavior, but these are impulse responses, this one and this one. A step response will still be exponential, but the steady state value will not be 0. Concept of control, a little bit about what this means. And by control, we mean automatic control. So you take a human out of the control role. So if you have your system, you have your plant, and you want to control the output. So what you normally have is, if you are applying an input, like you think about that spring mass damper system, you apply a force expecting the mass to move by a certain distance. You expect a certain x. Okay. Now, if you know exactly the parameters, if you know the mass, damping coefficient, and the spring stiffness coefficient, then you can predict exactly what the displacement is going to be. Not only displacement, but you can predict the behavior of that mass. Is it going to oscillate? Is it going to exponentially reach the steady state value? But you have, in real life, you have situations when some of the parameters change or some of the circumstances are not predictable. So if that system, spring mass damper system, is to represent suspension of a car, it will be different. That stiffness K will change slightly with temperature. The mass of the car will change depending on how many passengers we have in the car. And so on and so forth. So there are so many things you can't always predict in real life. So you don't always get the output you want. Not to mention there are some perturbations that, again, we don't model with a block diagram like this, but they may be present, and again, change the response, change the output from what we want to something we don't want. So one of the ways to solve those problems is to continuously monitor the output. So whatever this variable is, you use a sensor that monitors the output. Converts that measurement into a usual electrical signal, doesn't have to be.
And so this way, the output is compared with the input. In this case, the input is the desired output. So you just decide what you want your output to be, and this system, this loop, monitors whether the output is really what it is supposed to be. If it is exactly the same, so if the output is exactly the same as what you want the output to be, then this difference will be 0. And our plant works in a steady state mode, doesn't change anything, so maintains a constant output. If for whatever reason the output changes, then there will be a difference. So the output and the desired output will not be the same. Actual output and desired output will not be the same. And therefore, this error signal will not be 0. So error signal now drives our plant, our system, to correct the output until it becomes, again, the same as the input, the same as desired output. So in a control system, the input is not just an input. It is a desired output. So you tell the system what you want. And then this negative feedback loop should, ideally, execute what you want. So the output should be what you specify here. An example would be, I don't know, temperature control in the room, which reminds me. Air conditioning. Oh, it's running. It will stop in half an hour, so could you remind me to activate again? OK, so I assume when I press start, I'm actually telling the system I want 20 degrees. If in reality we have 25, then we have a sensor somewhere, temperature sensors, measuring that temperature and comparing with what I said I wanted. So if I said 20, and the sensor is telling it's 25, that difference will dictate how the compressor is going to work, or whatever we have in our air conditioning system, to reduce the temperature down to 20. Okay. And when the compressor starts reducing the temperature, when it drops down to 22, then this error becomes less. So there is less demand on the air conditioning to change until we eventually reach exactly 20. If we have an overshoot, so it drops down to 90, now suddenly this error becomes a positive number. Okay, so now our system is trying to lift the temperature a little bit. So it is possible to have some oscillations, but eventually, if the system works well, we will eventually have the output exactly what we specified by setting the input. Another system you may be familiar with is a cruise control for many cars nowadays. So without the cruise control, what you do is you use your pedal to adjust the speed of the car. So if it is a 60 speed limit, of course, you don't want to be faster than 100, OK? You want to maintain 60. And all you do is actually watching the indicator and pressing the pedal, or pressing or releasing the pedal. With the cruise control, you actually tell the car, tell the system, I want 60 kilometers per hour. And then you don't worry about the controls. You don't worry about the instruments. What your system does is you have a sensor monitoring whether you're really doing 60 or not. If you are, then the RPM of the engine or the fuel intake into the engine remains constant. Nothing is changing. So your engine, through the gearbox, blah, 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 maintains 60 degrees. If anything changes, for example, you come across a hill, okay, then obviously the car will slow down. Your sensor will notice that now you're doing 55, and there will be so this is where the difference is generated. This error signal will tell you it's 5 kilometers per hour less than what is required. That will increase the fuel intake, increase the RPM of the engine until you reach 60 again. So you have many systems like that everywhere around you, in industry, in everyday life, where actually you have a sensor controlling the output. All you need to do, all the human operator has to do is set the input, and by setting the input, once again, we mean a desired output, telling the system what we want, and as I said, the system is going to do it if everything is fine. That's the idea of control. Apart from that, there is no more talk. We'll do an example or two in a minute. What follows, this last page of lecture 9, is not going to be in the exam, and yeah, it's just there. So I will explain quickly what this means. What is the sensitivity? What is the meaning of sensitivity? When you have a system and it's running for a long period of time, there will be changes. So some of the parameters will change. I mentioned that spring mass damper system. If it is working outdoors, you may have some corrosion, so the mass will increase. Or you may have some physical damage, so the mass will decrease. That spring, that keeps, being extended and compressed, after a while will change its stiffness. So that K is not necessarily constant. It is constant for a particular short period when you observe it, but over a few years, it is not going to be the same spring, the same characteristic. The damper, the oil might leak, not much of that, but enough to change C. So the system itself may deteriorate. If you apply a feedback loop like this, a negative feedback loop like this, so this control loop should also take care of that, should reduce the effect of the deterioration of the system. Okay. Now, the whole thing is sensitive to changes, of course. But what that page is saying, effectively, is once you have a control loop, the changes in the system or in the plant have much less effect than changes in the sensor. So it is, in other words, it is possible to successfully control a very old, almost dysfunctional system if you have a good sensor. So the sensor has to work well, and the control loop will work well. However, if you have an unreliable sensor, no matter how state-of-the-art system you have here, the control loop will not work as well. So the control system is much more sensitive to changes in H than to the changes in G. Okay. And that's pretty much all what we are saying here. Right. But as I say, sensitivity will not be included in any of this mid-semester nor in the final exam. But you need to have an idea what sensitivity is. And there is, I think, in set 6, yeah, maybe I should open it. Okay, it is this question 5. You see, part A, you asked to find the sensitivity. You don't have to worry about that one. Okay. That won't be examinable. Right, now, if you remember, this is now lecture 5, that we didn't cover this particular example 6, and we didn't at that time because this is an example of a control system. So this system controls height, controls the level of water in this tank. How it is done? Now you have a flow in, you have flow out, and obviously you have height. Now here you have a float. This float acts as a sensor. So as I said, electrical, but not always electrical. So this float acts as a sensor because as height changes, so this float moves up or down. This lever here, so if the float moves up or down, this point here moves down or up. As this point moves down or up, it controls the valve, which in turn controls the flow in. So if your height is exactly what we wanted, then we will maintain constant QI, constant flow in. If height drops, then this valve will open a bit to allow more flow in to increase the height back to what we want. Or vice versa, if you have too much water, if height is higher than what we need, through this lever, this valve will close a little bit to reduce the intake of water and to maintain the desired height. Okay, so this would be an example of a control system. Okay, so let's now write equations. Some of them are as before. So you have flow in and flow out. So we can call it net flow. QI minus QO is the net flow into the tank. Net flow into the tank equals to rate of change of volume in the tank, which is AH dot. So this part is not different from what we had before. Flow out is H over R. So you have R, this valve resistance R, so the flow out will be proportional to height. Okay. Now this part, this displacement X through this lever will be equal to the difference between the desired height and the actual height times A over B, simply the leverage coefficient. But the important thing is X is proportional to not height, but the deviation from the desired height. So how much height, actual height, differs from the desired height. Okay. So now we can easily combine all these equations. So AH dot equals to QI minus QO. But QI is a function of X. So we call it KV, the characteristics of the intake valve. So we have KV where are we? Okay, KV times X, which is A over B, HD minus H, and then minus QO, which is just H over R. And effectively, this is the differential equation. We can rearrange a little bit so we get H terms on the left and HD terms on the right. Okay. What follows is pretty well known. Laplace transform, assume initial zero conditions, and we are going to assume also that the desired value is applied as in the form of a step. It is very hard to show in this system where you actually apply it. So we can imagine it is this valve that maybe you tighten a screw or loosen the screw. And you do it quickly enough to assume that it resembles a step function. Okay, so the desired value is a step function, but HO is the, excuse me, is the desired value of the height. So what we want to achieve. Okay. We also put some simplification, so we introduce K instead of all this thing, and we also introduce K1. Instead of these things. So output H will be equal to K1 over S brackets AS plus K. We normalize this expression and find the inverse Laplace of H of S. And that will be equal, H of T, K1 over A, and then 1 over A, which is A over K, brackets 1 minus E to the power minus K T over A. So a well-known exponential term, exponential function that we've seen before. A first-order system response of a first-order system to a step function. However, there are some peculiar things here. Now, we just said, maybe 15 minutes ago, that this system should bring the height back to the desired value. Is it so? Let's see what happens here. When time is infinity, this transient part will be 0. So we end up with a steady state value, which is here, or which is here. The desired value is HO, but the steady state value is not. Depending on what numbers we have down here, we definitely going to have something greater than 1. If it is greater than 1, the steady state value will be less than HO. Okay. It says as long as R is positive, but it's also true as long as A is positive, as long as KV is positive, as long as B is positive. Now, when you have a lever, you can't have negative A or negative B. KV, characteristics of the valve, cannot be negative. Resistance of the valve, R, cannot be negative. So effectively, H never gets to HO. So let's see the graph. Let's see how the whole thing looks like. The response is an exponential function. The steady state value is here, HO over 1 plus B over KVAR, which is less than HO. Time constant shows when we reach 63% not of HO, 63% of the maximum value, which is this value here. And the value of the time constant is 1 over this. So why is this happening? Why can't this system reach the desired steady state value? Will be explained in lecture 10. For time being, not every control system works the way we want it. There is something inherently deficient with some feedback loop systems, with some control systems. Yeah, what we also said, this model works only if the, H is less than HO when we apply that step input. If H is greater, then we have to model the whole thing from the beginning. It will be a slightly different thing. Any questions? Okay. Now you have this system addressed again in lecture 6 with the block diagram. I will skip that because I want to start the revision, if you don't mind. And the revision, once again, we will start with the past paper and then move to set 7. Okay, here it is. So as you can see, it is a very familiar system. So we are not spending too much time explaining. The only difference between what you had a couple of weeks ago and this model is that we have a conversion factor in this case that defines how much of heat is converted into, no, how much of mechanical power is converted into thermal power. So when you press this braking block against the moving disk, of course you generate friction, therefore heat. But in reality, that mechanical energy, mechanical energy can be converted not directly into thermal energy, but can also be converted into, deformation of the block, deformation of the disk, What else? Even sound. So there will be some losses. Okay, that's what this capital H is. The question here, so this question obviously nicely combines some modeling with the block diagram. Apart from block diagram, it's not too difficult. Maybe actually I should switch the camera. Okay, here it is. Now, if I remember well, it was obviously when? 5 years ago. But part A, complete the block diagram. So write the appropriate transfer functions in each of the block. If I remember properly, for each block, you get 1 mark. So part A was 4 marks. And I believe the easiest part was this, even if you know nothing about this thermal problem. If no one tells you what kind of system you have, you know that if you're going from theta dot to theta, what are you doing here? You are integrating. So it's 1 over s. So if you know this much, it's 1 mark. That this has to be an integrator. But in fact, I don't think I have enough room there. So the input is a force. Here you have 2 different rates of heat, one subtracted from another, to give us the rate of change of internal heat. So this is what generates heat, what brings the heat into the block. And that is mechanical power, so force times velocity. Force is already here. So it is, but the force that generates heat is friction force. So it's mu F times velocity and times the conversion factor, because this is heat. This is temperature. So what takes the heat out of the block is the heat released from the block into the atmosphere. That's what cools the block. So heat released into the atmosphere will depend, just one more point here. Theta is actually the difference between the temperature of the block and the temperature of the ambient. So it is theta times A, which is the area of the block, and small h, which is the coefficient of heat transfer. How did we call it? Yeah, heat transfer coefficient h. So the block loses heat to the ambient through surface A with heat transfer coefficient h. And what is left in here, so what is on this line is the rate of change of internal heat. Apart from, we have theta dot here. So rate of change of internal heat is mc theta dot. So we just have 1 over mc. So that will be a full block diagram. Question B, find the transfer function of the system by applying rules for simplifying the block diagram. So this was part A, part B. I believe this is really simple. Should we waste any time for this? You multiply these two, and then you apply a negative feedback loop. Maybe we should do it. Mu VH 1 over MCS. Oops, sorry. AH theta dot. A negative feedback loop, mu VH, G1, G2. Up here it's 1 over MCS. Down here it's 1 plus, again minus sign here, 1 plus AH over MCS. So the transfer function eventually will be MCS plus AH. So we have 1. So we have mu VH. The rest, I'm not sure. This was rather practice for a block diagram, as simple as it is. Doing parts C, D, and E will be effectively repeating the quiz question. So I don't think we should do that. After all, you don't expect the same question in the test. So let's do question 2 better, because it's something a little bit newer to you. So here you are given a response or a mechanical system acted upon a unit step input. So we are not telling you what kind of response, what kind of system it is. It is a step response. But as you can see, we are asking you to estimate the time to the first peak and the percentage overshoot, and hence calculate the settling time. So estimate from the graph the time to the first peak and the percentage overshoot. This way, we are already telling you that this is an underdamped system. And if you look into the graph, therefore my initial question, you need to have an idea how the graph looks like when you have an overdamped or underdamped or critically or even undamped system. And this is an example of an underdamped system. So you have some oscillations that disappear after a while. Therefore, you have an overshoot, you have the first peak, second peak is really small, and the third one is invisible in this graph. So it is an overdamped system. So transfer function. Sorry, we are still not working about transfer function. So it is A part 1. Estimate the time to the first peak. So it looks like 8. TP equals 8. If you think it's 7.5, that's OK. You're reading from a graph. Estimate the percentage overshoot. So steady state value, so percentage overshoot is M peak minus M, which is steady state, divided by M, and then times 100. Now, MP looks to me 3.3. M, the steady state value is 3, divided by 3 times 100. And that will be what? 10%. Oh, sorry, yes? It is underdamped. It is underdamped, yes. So this would be 10% overshoot. So that's the answer. So you have these two things answered. Now, third thing is settling time. Settling time, where is the page? Settling time is here. 3.91 over psi omega n. But we don't know psi, we don't know omega n. So we need to find those. Now we are definitely sure that it is an underdamped system. Okay, so how do we go about psi and omega? From the percentage overshoot here, we can write, let's rewrite this, m% equals 100 e to the power of minus psi pi over square root of 1 minus psi squared, which is 10. So we have exponential of minus psi pi over square root of 1 minus psi squared will be equal to 0.1. Logarithm on the left-hand side, natural logarithm, minus psi pi over square root of 1 minus psi squared will be equal to, according to my calculations from 5 years ago, is minus 2.3, which means you have plus and plus on both sides. If we multiply by this square root and then square everything, we'll have psi squared pi squared will be equal to 2.3 squared of 1 minus psi squared. From there, you have psi squared brackets pi squared plus 2.3 squared equals to 2.3 squared. And when you put everything into the calculator, approved calculator, of course, you get 0.35. So now we know the damping ratio. Time to the first peak is given a little bit indirectly. It's pi over omega d. Omega d is damped frequency, but it's given here. So actually Tp equals pi over omega n square root of psi minus 1 minus psi squared. So Tp equals pi over omega n 1 minus psi squared, which is equal to 8. From there, we find omega n to be equal to pi over 8 square root of 1 minus 0.35 squared, which is, again, according to my calculations, 0.42 radians per second. So finally, Ts equals to 3.91 over 0.35 times 0.42. And it is equal to 26.6 seconds. Okay. Everything okay so far? Okay, now part B, determine the transfer function of the system. Sorry, part 2, still part A. 2. This is the transfer function. We know psi, we know omega n, we don't know k. But what we do know is the steady state value of the output. Okay, so if y is our output, y of infinity equals to limit when s approaches 0 of s times y of s, which is equal to limit s approaching 0 of s times input, which is 1 over s. Okay, it's a unit input, unit step input, times the transfer function, which is k over s squared plus 2 psi omega n s plus omega n squared. Which is equal to, we are losing s and 1 on s. This is 0, so we end up with omega n squared, k over omega n squared. K over omega n squared, which is from the graph equal to 3. So k equals 3 omega n squared, which should be equal to 0.53. Now we have everything. So g of s equals to 0.53 over s squared plus, substituting the values for damping ratio and omega n will give us 0.29 and plus 0.18. Okay. No questions. And part 3, without reading, without estimating or calculating anything, just sketch the impulse response of the same system. So in this case, y, let's say capital Y of s equals to the transfer function times impulse, which is the same thing, 0.53 s squared plus 0.29 s plus 0.18. And we already know this denominator cannot be factorized because it is an underdamped system. We can check the tables and realize that we are going to have a product of an exponential function and sine function, because we are asked only to sketch without any numerical values. But, sorry, so y of t, maybe I should write it. Y of t will be equal to, when checking the tables, just to write as accurately as possible, Laplace transform tables. Okay. So check case 22. It is omega n over square root of 1 minus psi squared e to the minus psi omega n t times sine omega n square root 1 minus psi squared t. So this is from the tables, case 22. Okay, we have a constant, we have an exponential, and we have a sine. So we have an oscillatory input. The amplitude is decreasing. Eventually, this will settle at 0. So this response oscillates about 0. So it's like this. So you have these two exponential envelopes forcing the oscillations disappear to 0. And this is all. We are not interested in this value. We are not interested in the periods, frequencies, or whatever. Just sketch the response, impulse response. Okay, any questions? We'll continue on Tuesday with this, and then we'll do some examples from set 7. Oh, yes? Oh, in this case, then the question, okay, in this case, if we are interested in this value, then we will ask you what is the magnitude of the first peak, or what is the largest amplitude, or something like that, and when does it happen? So it will be clearly asked. When you say sketch, we want to see, do you know it's oscillatory? Do you know it settles at 0? That's pretty much all we want to know. Do you know, first of all, do you know it settles? Do you know those amplitudes are going to 0, and is it oscillating about 0, or is it oscillating about some other value? So that's what we are looking for. That's what sketch is. Don't worry about numerical values. Otherwise, we will ask clearly, we want numerical values. Yeah, okay. Anything else? Okay, good. Let's have our... Now, if I ask every third row to be free, don't go home. Just go somewhere else in a different seat. Like last week, I said, well, please leave every third row free. Well, everyone was gone. Okay, so our demonstrators, some of them are already here. The others are coming, so we can answer your questions. Sorry, let me just unchain myself, and then that's right. This one is okay.
Excuse me, I think one of your answers is not correct.
Sorry? Oh, you mean numerically?
Yes.
Okay, possibly, yeah. Possibly. I said I calculated 5 years ago when I was a little kid. So I didn't know how to use a calculator. No, it is possible. I think that's why I put that reservation, because what I think I did, maybe I forgot, maybe this is still square.
Yeah, this is square.
Yeah, okay.
And
so
that's why
that changes everything.
Yeah.
But that's okay.
That was my question,
Yeah,
because that's 27 seconds.
I get
And
13.
if you look at the graph, like it's
Yeah,
all over.
it's really too long. I agree. It's not logical. But that's a good feel. Good feel for, that's what I'm really happy to see, that someone, even if you guys make a mistake like this, that you see that it doesn't look right. A little comment here, this looks too long. Would actually get you some marks back.
Yeah, that's
Yeah. Is that what you want to ask? Yeah. Okay, yeah.
By the way, I'm in aero course now, so the simulation room is still like...
I checked yesterday, there was a guy on the ladder fixing something on the roof.
So it's like
So until we say something, no, nothing today.
Okay.
Nothing today. Wait, you have to book again once we provide new slots.
Hi, Zoran. Just regarding some of the trig questions,
Yes.
which are on that sort of topic.
Yeah.
Some of the trig answers don't actually use those approximations for the transient peak.
Which ones?
I think it's question 7 in particular.
Question 7 on which set?
Set 5.
Set 5. Question 7.
Yeah.
Okay. So what do you mean they don't use?
So I've got my transfer function, right? And I've plotted it on the graphing calculator, and finding the transient peak time and the overshoot or the maximum pressure. I can find it fine plotting it on the graphing calculator. But using the approximations, I get a different value.
Okay. Yeah, the funny thing is, I have to check, so you're talking about the number I gave you, the answer I gave you with what you calculated. Okay. The number I gave you, those numbers are not 100% guaranteed. They're 95% guaranteed. So I will have to check how I calculated. Approximate way to calculate is to just ignore exponential and say when sine equals to 90, the argument of sine is 90 degrees, that's where you have the peak.
Okay.
But that's not it. When you multiply by e, something happens with that
Yeah,
peak.
it shifts over. So
That's
the
right.
answers there are actually the exact answer, as opposed to the approximate. approximation?
I don't remember anymore. I probably have my.
I was just going to ask as well, in the test, we're just expected to use those approximations, not...
I will say, find the approximate value of the peak of
We're not
5.
expected to do product rule and differentiate for 20 minutes.
I will have to decide on that, whether I want you to do that or not.
Okay.
It's not that. I want to see whether you know what approximate and accurate is.
Because, yeah, the answer in the 2 questions suggested that you have to not use those approximations.
Yeah. Well, you're right. I mean, depending on what I want to test, if I want to test how you differentiate a function like this, then yeah, I will ask you for an accurate. But apart from that, if not, then I'll ask you.
You'll say approximate when you want us to use those. Okay, makes sense. Thank you.
Sorry. Oh, sorry, you lost something. I thought you knocked it. That's the final value, that's the steady state value. That's what you do. That's what you do in reality. But before that, you need to know that your system will produce a steady state error. The last lecture is actually called steady state error. So we'll learn more about that. Some systems have steady state error, some don't. Okay. Depending on, you will see what depends. But in reality, that's how you design it. If you know it is a first order system that will have a non-zero steady state error, then you actually offset. Well, that's what this example that I told you not to worry about the part A. If you check the other things, you will see that actually there is a steady state error here. Because you want to control speed of the car. And you set the desired speed like a cruise control. Okay. So what you do, you actually offset, you don't know as a driver, you don't know that, but the engineer offset your input by how much error you're going to have. Because the error is predicted. Fortunately, it's not good to have a steady state error. Fortunately, we can predict. We can calculate in advance what that steady state error is. And it will depend on actually these numbers. So you offset your input by that much. So when if you are setting 60 on your cruise control, it's actually setting, I don't know, 62.1 or whatever. But you as a driver, you know, you take the 60 look at it, if it is overdone, there will be no peak. It will just exponentially, as we showed in those examples.
Same thing happens for
Filter damp and overdone, they look similar. So I can't ask you to guess that from the graph. Because filter damp is just quicker than overdone. They are both exponential. So it's hard. I mean, I can't ask you that question because you can't tell what you can't tell. But other than we can tell, so I don't have to tell you, you have to know this. It's at 6. Yeah, which is let's go. First, okay, very good. Yes. Oh, okay. No. Okay, it is the steady state when the transient part does not exist. Everything, after the exponential becomes irrelevant, you have a steady state. Now, because your input is oscillatory, your output will be oscillatory as well. Like we said something. Yes. Okay. So this is actually what you do. Or this is the output. This is the full output.
Oh, okay, okay. At 60, Henry, you can regard it as your zero, your datum value. Yeah, in that case. So then you apply cosine, and then the sine also oscillates about 1, 0. So you can regard them as a reference. Yeah. Okay. Yeah. So that part, so you ignore that. Ignore that because that's the pre-zero conditions. That's initial conditions that when you derive transfer function, you're returning to 1, 0. So that's the reference pressure level at the other. Okay. Now, if this is the output, this one is gone. We are not showing. So what you are having is cosine with the constant constant. That's right. But otherwise you make it. Yeah, you can say if you want to be strict and say, well, it's actually steps and the cosine. Then your analysis is a little complicated. It's much easier to say we are working in terms of incremental variables. So this is 60 is our 0, and we are always working with the. Yeah, but well, yes, but in a way they should know by now. They should know that. By now they should know. I mentioned because with all those thermal problems, every time we say now ambient temperature with regard to be 0, and that which doesn't mean 0 degrees Celsius, just our 0 for our problem. So I said that so many times that I will say to the exam, right? Tell them that, you know.
In the mathematical
but the important thing, once you set this as the diamond value, amplitude is this. And some of them make a mistake, say the amplitude is 80. No, amplitude is 20. And the other amplitude is 1.5, not 6.5. So you measure from the reference value, not absolute value. I was thinking, Sean, did you tell Marianne about this?
I didn't.
Okay.
But what I was going to do was, when I fill in the timesheet for both tests, I'll just take an hour.
Yeah, that's what I want to suggest because it's too much paperwork. And it's easy that. Yeah, thanks for that.
I was going to wait to fill in the other one until after the second
Not
test.
doing any because a few other demonstrators are also missing classes, but I subtract that from their marking. And you're not doing any marking this year, so
I haven't filled in the timesheet yet because I was going to wait until after the second.
it's easier that way. Easier on Marianne.
Yeah, no, it's a waste of time.
expecting more technical, to be honest. I was hoping to get more technical. It's interesting, yeah, okay. Yeah, it's an interesting life, interesting career.
How many people in jail? I was like, I've never met any Soviet pilots, like Soviet aircraft.
No, yes, it would be like...
I'm not sure.
Was not. 5 question standard. You have
So to the start, this is 3 of set 5. I have removed the initial 5. Yes, 5.
we are planning for the latter part. No, set 5 question standard.
7 is here.
Only yes. No, you need to. No, this is minus. This is minus. This is minus.
Yeah, this is minus.
This one on the bottom side.
Yeah, you are signing where you start from here.
Oh, why? Question 3, set 5. Oh, why we are? Who knows? It doesn't matter.
So if it's not mentioned, it's a constant p, then it should be a step.
Yeah.
Of magnitude p. Yeah.
As long as it doesn't mention like impulse.
I have a very version from the explanation was about this. It was just a simple beam. Because every yes, so we have to calculate this kind of stuff. So the experimental value is equal to 3 also. And the so what we have to do is to calculate the formula. And given that the that's right, right?
About this actually.
Yeah, no. All this
try. What do you recommend? You need to look at the derivation, I think. So where is the derivation? This is not important. No, that is important because you need to know which eye you want to use. But the idea is if you want to keep because they will if you are see W is in because maybe you are using a different math. Or you need to look at the derivation.
Is it because good students or because they become good because they are coming? We don't know that.
I think it's more the good students who come in different. I personally, like, I went to my first class of physics, and I got told I was just like, this is the definition of doing this, it's sort of, and a lot of people would ask us questions about the lecture note, and I'm like, well, go and do it, and then I should be teaching you how to do it.
So were you there when I passed the paper? I'm not sure. Because I remember Ben Fraser, a very tall one. He had a little bit of speech impediment, but very nice guy. He's not there. He wasn't there. I remember him from. But you were not, or you were there when I passed the paper. You got. I don't know. I think it was the year before you. Usual mistake. I mean, okay. Yeah, okay. Some students don't see it. Okay, sorry to ask that. But in fact, you have three feedback loops. So one plus H2 times what you have up here. No, it looks right.
Yeah, I was trying to see maybe using this one, but it didn't like
That looks right.
really do it in this one. Okay, so you have S in the denominator. Doing this one times S, you can
Multiply that. Yeah, okay.
And the limit is for the same.
Also, I moved.
Okay. Thank you.
Yeah, you're right.
Yeah, so I've got B3 now coming to this as a negative feedback loop. So I apply the same rule. So here I'm reduced, so now it's just one big feedback loop.
How wrong? You have minus or plus, because I think you should have minus if I remember the problem. But
Yeah, this does a minus, that's a minus. So I've got
no, may I suggest something? You can check if you take this and this as the another parallel. Okay, you have one less feedback loop to deal with. And if you get the same answer, that means you made a mistake earlier. If you get different answer, so you probably made a mistake in the last one or two steps. That part looks right to me, if I remember it right.